Hello and welcome. This is the Taming Wild AI channel where we bring AI technologies out of the wild using the best practices of software engineering. A few weeks ago, we started a survey of the models in Torch Vision, a computer vision library. Some of those models had been discovered using neural architecture search. The latest used a technology called the transformer. The transformer was introduced in a 2017 paper titled "Attention is All You Need." Back then, it was applied to machine translation. Since then, it has been adapted to a variety of natural language and even computer vision tasks. Recently, it's gotten a lot of attention because it plays a critical role in ChatGPT, where GPT stands for Generative Pre-trained Transformer. There are numerous tutorials and videos introducing the transformer. For example, there is the Illustrated Transformer by J. Alamar. However, I'm more interested in implementations of the transformer. I find it difficult to read complex mathematical equations, and I'm always suspicious that implementations of equations are more complex and tricky than they look. The online book Dive into Deep Learning has a chapter on attention mechanisms and transformers with code snippets. Similarly, Sasha Rush, Austin Huang, and others published The Annotated Transformer with code snippets illustrating the original paper. These notebooks are truly great for educational purposes, but it becomes an exercise left to the reader to glue everything together to make a useful technology. My favorite tutorial is Transformers from Scratch by Dutch professor Peter Bloom. His explanations and insights on the ideas behind the transformer are unequaled in brevity and clarity. Not only that, his illustrative snippets are made available in a complete code base that trains and validates a sentiment analysis model on the IMDb dataset. Let's give it a try. Let's clone the repository. And switch over to Visual Studio. Here I'm going to create a virtual environment. And let's look at the README. All right, I'm really pleased to see that Professor Bloom has concerned himself with dependency management. His first instruction is to run a simple pip install command. All right, that worked. And then he says to run this command. All right, so there is an error, and it is at this line. Let's just uncomment this and see if that works. All right, I did a little searching on the internet, and it turns out that the pip install command installs the latest version of this TorchText library, but the classify.py script depends on an earlier version. So let's try installing that earlier version and then run the classify.py script again. Looks like it's downloading a data set and it's training. All right, so 80 epochs were run and each took about 12 minutes. That's a total of 16 hours on my Mac Mini. The model achieved a validation accuracy of just over 85%. Let's see what actually happened in this code. I'm going to take a top-down approach to how this code works because the bottom-up approach is already covered in the blog post. This script has an if name equals main construct for modularity. These lines parse the command line arguments into an options variable that is printed and then passed to the main function go. Go loads the IMDb dataset and then creates an iterator for the training set and an iterator for the test set, either here or here, depending on the value of this command line argument. As this description shows, the IMDb dataset consists of highly polar movie reviews and a binary sentiment for each of them. Back to the code, it creates the transformer model and the optimizer and the scheduler. The training loop executes for a number of epochs specified in the command line arguments. For each batch of training data, the output of the model is generated, the loss is calculated, and a backward pass is performed to adjust the weights in the model. At the end of the epoch, the script goes through the test set. For each batch, it calculates the output of the model and then accumulates the number of correct classifications. At the end of the testing epoch, it prints the accuracy of the model. With very little effort, Bloom's code was able to achieve 85% accuracy on this task. I did a quick internet search for state-of-the-art accuracy on the IMDb classification task and found this page. The top performing algorithms are dominated by transformers. So not only has Bloom explained transformers extremely well, but his code is easy to read, well documented, and modular. It executes successfully and reaches accuracy within sight of the state-of-the-art. Instead of spending time just getting the original code to work, I can spend it on understanding the refinements and tricks others have used to achieve state-of-the-art accuracy. Andrej Karpathy, one of the founders of OpenAI, has a 2-hour video titled "Let's Build GPT from Scratch in Code Spelled Out." Karpathy delves pretty deep into the technical details of GPT, including aspects beyond the core transformer technology. He provides a Google Colab notebook for the video. He also provides a GitHub repository for the code he writes. Not much of a README, but let's take a look. We'll start by cloning the repository. Now we'll create a virtual environment. And let's try running this script called gpt.py. Alright, unfortunately he has assumed we have the correct version of PyTorch installed. Let's see if it works with the latest version. Alright, it seems to be doing something. Alright, it looks like that took about 10 hours and it went through 5,000 steps of training and then finally generated some text that, looks surprisingly like Shakespeare, although it doesn't make much sense. Anyway, let's see exactly what this script is doing. Right off the bat, we see a number of global variables. There are some functions and classes, which is good, but there is no use of the if name equals main construct. That's unfortunate because it'll make it more difficult to reuse this file in another application. The script opens the input file, which I think is the complete works of Shakespeare. There is an encode function which takes a string and generates a list of integers as input to the model. There's a decode function which takes a list of integers output by the model and generates a string from it. The text is split into 90% for use in training and 10% for use in validation. This function generates a batch of training data. The examples are character sequences of length block size, randomly sampled from the text. And the labels are character sequences of the same length, but one character ahead of the start of each example. This makes it clear that this is a character prediction model that can use one or more characters as a prompt. Now there are several classes that Karpathy has explained and developed in his video. The script instantiates the model and an optimizer. In every iteration, it retrieves a batch, generates logits and loss from the model, and runs the backward pass to adjust the weights. At specified intervals, it calculates the training loss and validation loss and prints these out. At the end, it uses a single character, whatever encodes as 0, as a prompt to the model. It uses the model to generate up to 500 characters from this prompt, decodes them, and prints them. The fact that this is a character prediction model explains why its output gives a definite Shakespearean impression, but includes many nonsensical words. In this video, we looked at a couple of excellent tutorials on transformers, which are a core technology inside ChatGPT. The code for these tutorials is relatively easy to execute and super easy to read. Peter Bloom's code has excellent modularity, but Andrei Karpathy's code was definitely meant to run inside a notebook environment. Thank you for tuning into this episode, and please stay tuned. If you found this video instructive or useful, please share it with others who might too. Don't forget to click the like and subscribe buttons, and I also welcome all of your constructive comments. Finally, if you would like to help out with taming more wild AI technologies, please drop me a note at the email address in the notes.